Thanks Dheeraj and all the local organizing committee for this wonderful meeting. I want to start by saying that I'm going to talk about something I know very little about. It's baby steps for me, just because the images are too beautiful to resist. Okay, so I'm going to talk about morphological complexity. So morphology, the word morphology is used in various contexts to mean various things. So here I am going to talk about basically the shape of galaxies, not exactly quantifying, but quantifying like in geometrical sense, but in the sense of measuring a statistical quantity called complexity. So this is a pilot study which I would like to in the future expand to many galaxies, and hopefully it will lead to a scheme for classification of galaxies. So this is the first step. And this work is done with Langlen, who is a postdoc in South Korea, EPCTP, and Amruta, who is a student in IIA. She is a student of my colleague Moshmi Das, but she is also my student. So, and Langlen was my intern student a few years ago, and Changbom Park from KIAS. Okay, so let me explain the context. So, all these statistical things, objects that we see in the world around us, they have order as well as disorder, some element of order and disorder. So, the subject of complexity basically tries to study or quantify these concepts. And so what I am going to talk about is, so when we say order, for example, I have put 3 examples here, starting from the extreme case of having a crystal which is perfectly ordered, all the way to an ideal gas which is completely disordered. Okay. So it has all these, there are many possible ways in which the individual elements of the object can be arranged. So that, that number of ways will quantify the disorder there. And we have objects in between like us, or any of the material around us, and to on the large scales maybe galaxies. Since my talk is about galaxy, one particular galaxy, this is an example which has order plus disorder. So if we, intuitively we think of a crystal as simple because it is, intuitively we know it's simple, right? We know how it is arranged and so on, and it has one state. All the individual components are arranged in a particular order. And also when we have an ideal gas, we know how to set up the equation thermodynamically or statistically. We know how to set up the equations, we understand the system, and so we associate the word simple to it. Then anything else that lies in between is here, they are complex, and it will be nice if we can quantify the level of order, disorder and complexity. So this is the context, and in order to do that, to quantify, so this plot here is just to tell, on the x-axis is like the different kinds of objects. What I mean by parameter is that, and we imagine some, we can think of some quantity or quantifying entropy for the disorder, and some quantity called complexity, which will go from here to here. So how do we set up that? And so for this, I am going to use a formalism which was basically initially set up by Louise Mancini and Calvet in statistical physics, and they developed some measure on which, so if I plot entropy here and I plot complexity here, I will just define them in a moment, and then I can classify various objects in between, where will they lie. So did I skip something? Okay. So that the ideas were set up in that paper, but the calculational framework was developed later by in a series of papers. So when we are dealing with data, then the idea set up by Louise Mancini and et al., that previous paper, that was a conceptual, how do you calculate states and so on, but it does not give the clear outline, algorithmic outline how to calculate. So that kind of outline was developed by using something called the ordinal framework, and I'll just explain very briefly what that does. So our goal is to, given a system which is a data set, I want to have a way to define a state, and I want to have a way to count those states, and from that I will build all these other physical quantities that I'm interested in. So in 2 dimensions, because I'm going to talk about galaxy, which I'm going to assume to be a 2-dimensional object. So we will have a matrix, for example, the intensity of the galaxy in different pixel locations will be numbers of this type. And so the way to calculate the states is to take, so here I am demonstrating with an example which is a 3x3 matrix. So I can define a subset of this matrix. Let's say I take a 2x2 matrix, first 2x2 matrix and then next one, and then go down and so on. So I will have out of these 4 matrices, and from here I look at the numbers, values, and organize them in ascending order, not in ascending order, sorry, in a particular sequence. Okay, first row and second row I organize. Then based on their I assign numbers, these are just placeholders 0, 1, 2, 3. Then I sort them in ascending order, and then how these numbers, the placeholders get permuted finally, that is what I call as a state. So I'll have 4 states here. Now this is just a 3x3 matrix. In general, when I have a large matrix n cross m, so I will call this dx dy. Here I use 2 and 2, so 2 cross 2, that is called the embedding dimension. And from based on that, given n, capital N and capital M, I can count how many possibilities are there and so on. And I can count, I can construct all these sets. So the set of all these sets, states that I have constructed is called the ordinal set. It will be indexed by where I can have I and j index to do that. And out of all these possible states, only some of them will be distinct. So this is in the case when I have a large number of states and distinct states are few. Okay. So there will be few distinct states. So for each distinct state, now I can count in the ordinal set how many times each one occurs. So this is going to be my basic quantities from which I can construct my observables. So from here I can I construct something called the ordinal probability, which is the number of times each distinct state occurs given by the total number of states. So this gives me a probability for the distinct states. Now I have the basic quantities ready, and these are the people who developed this further for calculation. So I am going to define an entropy from the probability that I just defined, ordinal probability, and then I have this is just a normalization factor. So the quantity, what I am going to call permutation entropy is this H, which is the normalized entropy. Then so that's the first step, which will measure the disorder. Then disequilibrium is basically so given the probability that I have just constructed, how far is it from equiprobable distribution, that I can measure that. That is in information theory there is something called the Jensen-Shannon divergence. So this is the telling what that quantity is, okay. And it is again normalized by a normalization factor, which I do not show because it is long. So this quantity, now if I multiply the entropy to this, then this quantity is called the complexity. So I am interested in H, DE and C. Basically I will be more interested in H and C, and I am going to ask, can I classify galaxies by measuring this for each galaxy. Okay, so today I will have one test galaxy, and that is this is the NGC 628. This is an image from JWST, and you can see there is randomness and there is order, there are structures and so on. So my goal is to quantify, calculate those quantities that I defined for this particular galaxy. Okay, so the questions are, I have already explained the questions. This is a big goal and this is the first step by using this galaxy. And what I am going to do is measure complexity at different length scales and across different wavelengths to see how does it behave. Okay, so regarding the data, so I am using archival data. So I chose this because I wanted to basically use UVIT data, and so also UVIT plus it should be available at many redshifts. Sorry, not redshifts, many wavelengths. And so these are the four, so UV, NIR, MIR and millimeter from ALMA. These are the three data that we use, and these are the particulars about the resolution. So JWST has a smaller field of view, UVIT has very large, so everything is brought to the same resolution and same field of view, and roughly in the parsec size my resolution is going to be like 20 parsec. And I will play around with these three embedding dimensions. So I can 10, okay. Okay, so so now let us look at the four images and in the four wavelengths. So in this is the UV image. So here I did not mention it here, but so this is smoothed with about 20 parsec resolution, all of this, so that they are all equivalent, and we are going to smooth it at different scales to see how does the properties change as a function of smoothing scale and across the wavelengths. So in this y axis and z axis is what we are interested. And just to have an idea, we plotted the intensity probability distributions of the intensities, and these are the kind of distributions we get. They are probably can be fit by log normal. Okay, so the one point to mention here is that clearly as we smooth to larger and larger scales, of course the small scale fluctuations are going to get washed out, and the images will go towards these well ordered kind of behavior. Okay, so it's good to take a look at the ordinal probability. So the ordinal probability I am showing here for the case of 2 cross 2, it will depend on what this is, and this circle, diamond and so on, they are representing different wavelengths. So so clearly you can see that they are differing from, I mean if I just focus this on the circle 1, so circle 1 is here 1, so they are clearly differing from equiprobable distribution, and the idea is to measure how far away from equiprobable distribution is it. Okay, so I start with the results. So first we measured is just to see how the entropy and the complexity behave. So as we increase the smoothing scale, these are in units, 1 means 2, the sigma is a smoothing scale, so 1 means 20, 30, 20, 40, 60 and so on, that is how it goes. And so you can see that the entropy decreases as you go to higher smoothing scale, this is expected, visually it is easy to see. Then the disequilibrium, whereas on the other hand the disequilibrium increases, and the complexity will be basically, C will be basically a multiplication of these two, and these are the kinds of behavior that we see. So now from here we cannot extract much physics. So to do that, let us look at, so my interest is in plotting the C versus H, using the C versus H as like a phase space place where I can say, okay, each galaxy will occupy one point. So here of course I am plotting, I have H on the x axis and complexity on the y axis, and here these arrows are indicating smoothing scales from smaller high resolution to low resolution, so you can see them behaving in this way, and these are the different embedding dimensions, so there is a dependence on the embedding dimension. So what stands out here is roughly these NUV, NIR, MIR, they have a sort of a similar behavior, whereas the millimeter shows a slightly different behavior. And we think that this is because the millimeter emissions are coming from CO J equal to 2 to 1 transitions, and they are cold and clumpy, and so they have a different behavior. So this is the one first thing. And then now I am interested in looking at across wavelengths. So I fix the smoothing scales, and then I look at, is there a systematic behavior? Do they occupy, behave nicely on the CH entropy complexity plane? And this is the what we have found. So let us examine little bit clearly. So at small scale, you can see they are all very, they are distinct from each other, the points. So this is UV, and it goes down to millimeter. So they are distinct. Now as I go to higher and higher smoothing scales, I find that they are now becoming, they are behaving in the same way and getting clumpy, and it is not, we are not able to distinguish any further. So now, just by visual eye, I want to quote this number, a quantification is being done, but I can identify some rough scale, maybe 80 parsec from here, which sort of distinguishes the behavior of the galaxy at, which is sort of the same for the different, it's a scale at which all the images at different wavelengths, they have similar properties, and above that, below that they differ. So the relating to the physics of the galaxy, so we know that the galaxy has stars, it has stars, interstellar medium, there is dark matter, and there is gas and dust and so on. So what we think is happening here to interpret physically is that so the random fluctuating nature of the distribution in stars and ISM, that makes a transition at this scale from the random nature to a self-organized behavior. And we think it is related to the size of OB associations. So if my knowledge is correct, OB associations, these are some kinds of stars, and they are clustered at some scale. And this, I think we can relate this to the size of the way those stars are clustered. So what is happening is that the stars will give out UV light. The UV light will stir off the interstellar medium. The light will be absorbed by dust and so on, and re-emitted in the other wavelengths. And so what the star produces is used to stir up and cause turbulence in the interstellar medium, and so there is a cascading effect, and that is what we are seeing here. Whereas it is very weak in the CO regions, which is what I showed you in the previous slide, CO regions, because they are already clumpy, they don't have much diffuse structure. Okay, so then finally, my interest is in looking for universal properties. So this is a plot where I have plotted all the wavelengths and different smoothing scales together. And what is interesting, we were not expecting this. What is interesting is that they seem to all lie. There seem to be a attractor trajectory here towards the smoothing scale, higher smoothing scales. There seems to exist such a trajectory where all these, which is specific to each embedding dimension, and they all get attracted towards that. So now this cyan colored line, this is what we did is we made Gaussian random simulations, white noise, and we smoothed to scales, different scales, to find is there some, does that give us a standard trajectory towards which all the other galactic properties will converge. So this is actually a Gaussian simulation of the appropriate size suitable for the images that we took, and we find that it fits very well. What we found, and I am not showing here, is this is an isotropic Gaussian random field. And if I change the isotropy, if I introduce an isotropy, then these plots are differing. And so this particularly specific to this NGC 628, it seems to asymptote to this behavior. Okay, so I think I am close to the end. This is my summary. I have just studied the morphological complexity of this galaxy, NGC 628, and this is the first step towards classification of galaxies. I am hoping to apply this to a large set of galaxies and see if there is how they distribute, particularly in this plot. Where do they lie? Thank you.
Questions?
Yeah.
Hi,
Yeah, okay.
Prabha. So nice talk. I have a question about the second last slide that you have.
Yeah.
Like if you have, if you look
one
at
or
the
previous?
the one previously. So, on this plane, have you tried to take images of different galaxies at in the same filter, say JWST or
We haven't done that.
UVIT?
Yeah.
Because if you take and say a very regular galaxy like an elliptical galaxy,
Yeah.
and compare that with say an irregular galaxy,
Yeah.
you should see very clear trends on this CH
Yeah.
plane.
Yeah, we hope to
if
do
you
that
if you
next.
do that,
Yeah,
then
yeah. Yeah.
you'll be able to
Yes.
at least confirm that what you're getting seems
Yeah.
reasonable.
Yeah.
One last question, if there is anything. Yeah.
Yeah.
How does the entropy defined, differ from Shannon entropy or Renyi entropy? Very naive question. So,
I don't know how those are defined. I know how this is defined. I mean, I need to look how those states
just
are.
what minus sigma p log b. Anybody else knows the?
I can tell you how the entropy is defined here. So the states are being, I think they would be related because see the basic thing, definition of the entropy is not the main thing. Definition of entropy is here. The formula is the same.
Formula looks the same.
Yeah, but the point is how do you construct the state and how do you count the state? So the state construction is here for me. This is a procedure in which I am doing so it looks at these permutation states, we call it permutation states. So look at neighboring neighboring intensities, sort them out, assign a state to it and find out all the distinct states and how many times each distinct state occurs. That is the way this is calculated. So I don't exactly know how to answer your question because I need to look up the literature and see how the state is defined.
Okay, I think we should move on. We're running late. So, thank you.